Today we're going to be introduced to a thing called enthalpy of formation. In particular, it's often called the standard enthalpy of formation, which would be with a little circle up here, which means it's done at standard conditions, which is 1 atmosphere pressure, all solutions are 1 mole per litre, 298 Kelvin, all substances are pure. Alright, so it also means though that if, for example, you're to be making water, it would have to be water at 298 Kelvin, so it would be liquid, not steam. So the enthalpy of formation tells us the amount of energy required to make 1 mole of a substance from its elements. So therefore there are no enthalpies of formation for elements themselves. Oxygen gas, O2, does not have a value. Carbon, whether it's graphite or diamond or coal, has no value. So if you're trying to use this information to find the enthalpy of a reaction, which is delta RH, then if that reaction has got oxygen or carbon or sulfur in it, then you don't have to worry about it because it's already been formed. We're making things from their elements. So one of the most common ones that you're going to see is the enthalpy of formation for water. So we go enthalpy of formation of H2O liquid, because that's what it is at standard conditions. And it normally equals, and sorry, I'm going to double check this, normally equals negative 286 kilojoules per mole. What this means is that we're going to make 1 mole of H2O liquid. Okay, so we need to be able to show it as a chemical equation, a balanced chemical equation. Well, H2O, it's obviously made from hydrogen. Now, hydrogen as an element doesn't exist as the atom. It exists as H2, and at 298 Kelvin, hydrogen is a gas. Oxygen exists most naturally as O2, and again, that's a gas. This, of course, is not balanced. Now, here's the key thing. It says per mole. It means per mole of water. There's already 1 mole of water shown. So I can't just double this and double this, double this and double this to make it balanced. I'm not allowed to do that. So how do I balance this equation? Half, good. Remember, these are not numbers of molecules. These are, they're not 1 molecule of this and 1 molecule of this. They're a ratio in moles. 1 mole of this plus half a mole of this makes 1 mole of this. The energy released there is 286 kilojoules per mole. Negative because that's released energy. Okay. By the way, this is also the enthalpy of combustion of hydrogen. Okay, so it's also delta C for combustion, H of H2 gas. So it's actually the same thing. Because combustion means the reaction with oxygen, the complete reaction with oxygen, and that's what this is. That's as far as hydrogen will go when you combust it with oxygen. So this actually has 2. It's both the enthalpy of formation of water and it's the enthalpy of combustion for hydrogen, because they have the same balanced equation for 1 mole of hydrogen being burnt or 1 mole of water being formed. So why do we need to know these, or how do we use them? Well, actually, a lot of reactions, we need to predict how much energy is going to be released or absorbed by that reaction before we do it. And we need a ballpark figure, if nothing else. So enthalpies of formation will actually give us that information. The enthalpy of a reaction, and the little r means reaction, so it's what you're usually going to be finding in a question. The enthalpy of a reaction is equal to the sum, so remember that symbol from our maths days, the sum of the enthalpy of formation of our products, because they're being made, minus the sum of the enthalpies of formation of our reactants. The reason that it's a subtraction is, of course, we're having to unmake the reactants, so that's why that has to be subtracted. So enthalpy of formation is a really useful thing for working out a theoretical value for the amount of energy gained or lost. Then when you do it in an experiment, you often find there's a difference in value, and that's because maybe it was not liquid water made, but steam, and that requires a bit more energy, okay, which we did in an earlier lesson when we looked at the molar heat of vaporization for water. It might be that some energy is lost to the surroundings and not actually contained in the system. So it gives us a theoretical value for the enthalpy of our reaction that hopefully we're close to what we actually find to be the truth.